Now we get all our functional data properly preprocessed and ready for statistical analysis. During the following hour, I will try to cover several important questions. We are going to consider categorical and parametric designs. We will see what is design metrics and understand how to read it properly. After, we will talk about hemodynamic response function, its time and dispersion derivatives, and in order to combine those, we will have to discuss T and F contrasts and respective contrast matrices, how to set them in SPM and how to use them correctly. Afterwards, we will run two-factor factorial design specification as it is described in SPM manual for this event-related fMRI experiment with known and with famous and unfamous phases repeated twice during the experimental session. We will learn to run statistical inferences. We will see statistical table of SPM and carefully examine different columns of this table so that everything is clear, how to use it and how to read it. We will try to build event-related Peri-stimulus histogram, again as it is described in SPM manual. Then we will try to set few contrasts manually using the same design metrics, and at the end we'll also run a parametric design model specification and plotting parametric response achieved during this using this model. But we are going to start from categorical design. What is it? Categorical design is modeling of different features of the stimuli as separate conditions. For example, we separate non-famous and famous phases. This is going to be one categorical factor. The other categorical factor is the repetition of the presentation. If the phase was presented first time during the session, it is one category of the repetition factor, we can call it like this. And if it is shown second time, doesn't matter if it is famous or non-famous, it is the second category. Let's see an example of how different stimuli, different events, conditions can be separated according to the categorical design. In this case, it is very simple, since we have two parameters, pretty arbitrary, but still we can easily see four different groups which are achieved by through combination of two different factors. One factor is easiness in this case, and this is one level of easiness, easy, and this is other level of easiness, difficult. Other factor is the taste. This is one level, tasty, and this is other level, untasty. And this is how looks the design matrix we are going to achieve after we properly prepare the model specification procedure. Let's run SPM and see how we are going to do it. In this case, we will follow precisely the instructions given in the manual for this practical example. Okay, this is the last part of preprocessing, smoothing, and after it we start with modeling or specification of our model. First of all, we have to load file sotmat. This file is normally in our working directory because it is the part of the archive file which we have downloaded in advance. We right click on it and press import data. Okay. Those variables is what we need. We click finish. Now we see those variables in the workspace. This means that we can use it in SPM. Those are important data about the experiment. In fact, this is where the timing of the stimuli of 4 categories are stored. Now, according to the manual, we click on specify first level. And we will go one after the other through different steps of model specification. Directory. We have to select categorical folder. At the moment, this folder is not created in our working folder, which is called face wrap, but we can easily create it. Okay, And now in the batch editor we can indicate this folder. This is where the SPM file will be stored and all the necessary images will be created during statistical analysis. Next, we indicate units of design. In our case it is scans. Interscan interval, it is 2 in seconds. Micro time resolution, if you remember, it is the same as in slice timing correction, 24, and the onset is 12. Now, data and design. We create new subject session and we select all the scans, all the functional scans, of course. We go to functional folder and we set the filter, but it is a bit different than it is here because the prefix during smoothing was S8 in our case. Then WAR is quite the same and correct at the beginning. There must be 351 smooth, normalized, slice time correction, realigned functional images. Let's select all and verify that it is 351. That's it. Now we click Done. Okay, the images are selected. And now we have to set the conditions. There will be 4 conditions. N1, N2, F1 and F2. The order is important. So we create new condition. And set the first name N1 and the onsets can be downloaded from the variable, which is, if you remember, now in the working space, because it was loaded from this file, this mat file. It is here, and we can indicate sort figure brackets and 1. Okay. Durations will be always 0 since our events are very short. Now, in conditions, as it is recommended by the manual, we replicate the condition we change the name to N2 and we change the onsets. This must be removed and we indicate sort 2. A more convenient way will be not replication but creation of new conditions. We need 2 more. In total we have 4 conditions. 2 of them are specified, 2 others are not. The first 2 are not famous first presentation and not famous second presentation. So now we will do famous first presentation, duration 0, and famous second presentation, stimulus onsets 4, and durations 0. For multiple regressors, we select the displacement parameters generated automatically and stored in the functional folder. There will be 6 parameters of displacement and rotation. And the last but very important step. No, we have 2 more important steps. Factorial designs. We create 2 factors. We call first one fun for famous, non-famous, and we indicate that there are 2 levels. The second factor is a repetition, and there will be 2 levels as well. How do we know the order of the conditions? We know it because it is written in the manual, and because we designed the experiment in the way that the order of stimulus onsets is exactly like this. First, 2 not known, not famous, first and second presentation, and after 2 famous conditions, first and second presentation. That is why we indicate it in this order, and this order is specifically important because, as we will see a bit later, only with this order of conditions our factorial design will work correctly. And the last step of model specification is the basis functions. Here we are going to add some derivatives, in particular time and dispersion derivatives. You will see clearly what it is just a bit later. Now we have to save the job. We call it 08 categorical specification. 08 is just useful to see clearly the order of steps of processing, since it will be sorted according to the name. And we run this. It doesn't take a lot of time, and voila, this is the design matrix, exactly as it is shown in our presentation, and exactly the same picture as expected according to the manual. But now we have to figure out what is the meaning of this table. What is the difference between different columns? How to understand those gray and black and white strips. And in order to do this, let's look at our presentation, where everything is explained hopefully a bit better and more clear than in the manual. Each column in the design matrix is one condition, or predictor or regressor. You can call it whatever do you prefer. And the alternative representation of this stripped column, which corresponds to the very first condition, which is non-famous first presentation, is here. This is time series plot. In red, you can see the onsets of the stimuli. Each stimulus, as you remember, was a short presentation of the face. The duration is exactly the same, and the interval is quite variable. In blue, what you can see is the expected bold response, expected hemodynamic response in the cortex. It is achieved from the convolution between the stimuli and the hemodynamic response function. We will talk about this a bit later. Let's review a magnified version of the first part of this column. And we can see that it precisely corresponds to the time series of the bold activity. The very first scan is indicated at the top, and then the direction of the time is from top to bottom. Here it is from left to right. This is the first expected response, and this is where it is in the design matrix. Here there are two presentations of the same category of the stimulus, and you see only one response, but it is bigger. This happens because the hemodynamic response is very slow in comparison to neuronal activation, and two responses just merge together and give you a slightly higher peak and a longer response. Here you see a combination of the three successive presentations, of the responses to three successive presentations. And this is where it is in the design matrix. As you can see, the line is very coarse. This happens because our sampling rate for functional scans is very low. Each scan takes 2 seconds to be recorded. Now you can see a combination of two of responses to two different conditions. In fact, there is an error in the presentation, but we can easily correct it. The blue frame shows sorry, another mistake. The blue frame shows the first presentation of non-famous faces, and red frame shows responses to second presentation of the non-famous faces. And this is how it looks if you overlay the responses in the same time series plot. At the moment, it is already a bit difficult to discriminate two time series. And that is why in design metrics, the amplitude of responses is encoded in color. The white color means higher, more positive amplitude, and the black color means something negative or low. As you can see, after each condition, there are two other regressors which correspond to the condition quite precisely in the timing, but they have different colors or different shape. And it happens after each condition. Not famous first presentation, not famous second presentation, famous first presentation, and famous second presentation. Those two are time and dispersion derivatives. In this particular case, for N1 condition. This is N1 canonical hemodynamic responses, and in red and green it is dispersion and time derivatives plotted. What does it mean, and why do we need additional predictors in this model? As you can see in this plot, the green, the time derivative, always arrives a bit earlier, and there is a negative undershoot component at the late part of the response. For the dispersion derivative, there is sort of sharp peak in the middle, and some low parts of the plot early and late. This is very important because this will help us to understand why do we need time and dispersion derivatives added in the model. This is a smooth shape of the functions. In blue it is canonical hemodynamic response, and in green and red two derivatives, time and dispersion. As you can understand from the name of those derivatives, they are derived, they are achieved via some mathematical transformations of the canonical hemodynamic response function. But they have those features of the latency and the sharpness. The problem is that hemodynamic response function in each particular case, is it a different individual or a different brain area or a different response of the same brain area, I mean different tasks, different stimulus, the hemodynamic response function can differ just a bit. For example, it can be shorter and it can start earlier or later. We don't know what is the specific mechanism of those variations in the shape of hemodynamic response. But to take into account this uncertainty, we can either add time derivative to the canonical response and we get something earlier, or we can subtract and we get something slower and later. In this way, we can model much more varieties of the shapes of the hemodynamic response. And since we don't know what is the specific shape in each particular case, sometimes it is useful to incorporate into the model this time derivative. Function. The other function is dispersion derivative. And in this case, what can be modified is the sharpness, the duration of the response. If we add dispersion derivatives, the response becomes shorter than the canonical one. If we subtract, the response becomes longer. But how can we use three different responses at the same time if we don't know what is the proportion? What are the coefficients for the combination of those three? It is possible if we use proper contrast matrices, and in particular for the combination of three different functions. For each response, for each condition, we will use F contrasts, which are very different from T contrasts. In general, both of T and F tests are very useful, but they answer to different questions and should be used carefully and appropriately according to their abilities. T-test shows one-directional effects, either increase or decrease of something respectively to something. It is much less flexible in this way, but more sensitive. The F-test works in a different way. It shows non-directional effect. Namely, we don't know if F-test is significant. Was it an increase or decrease? Which of the two samples had greater or smaller mean? We just know that there is a difference, some difference. In this way, F-test is more sensitive, but much less specific. And the interpretation of the statistical outcome for T and F-test will be different. Now let's run through some examples of T and F contrasts. The most simple option is a contrast with one value, which is 1. If it is T contrast, this kind of simplest contrast matrix tests the hypothesis that the condition, whatever is the condition, has a positive effect. If we do the same for F contrast, it will tell us if there is any kind of effect, either positive or negative. We don't know which effect, but some kind of effect is there if the F-test gives us significant outcome. Pretty similar if we enter two values of 1 in T contrast. But in this way, we look for the average effect of two conditions. A positive effect of two conditions, of the average of two conditions in case of t-test, and any kind of effect, positive or negative, for the f-test.